In this video, we will prove that the dual of any LP space can be seen as an LQ space for some Q. Let's state the theorem that we want to prove. So, theorem. So, suppose we have a measure space that is sigma finite. Measure space. And let's consider P and Q some exponents. So P will not be 1 and Q will not be infinity. So it's important. So we are not considering the case P equal to 1 and Q equal to infinity. And let's assume that these are conjugate exponents, namely 1 over P plus 1 over Q is equal to 1. So this is what we call conjugate exponents. So, and it's important to notice that for every P, there is only one such a Q, and vice versa. Okay? Then, what we will show is that LQ dual, the dual of LQ is isomorphic to LP. And the isomorphism is via the map for that for any element in LP, associate the element of the dual of LQ that to any element in LQ associate the integral of the product FG in the mu as an element in R. Good. So in particular, we will consider the case in which Q is equal to 1. So we will have that that L1 dual is equal to or isomorphic to L infinity, but L infinity dual is going to be much bigger than just L1. So we already saw in some previous video that this map here defines an element of the dual of LQ. Also in the case when Q is equal to infinity. But in the case in which Q is infinity, this will not be all of the elements in the dual. Okay. In the other case, this will be the case. So we only need to prove the surjectivity of this map that we defined. Okay, proof. So as I said, we already proved that the map that to any LP associate the map, let's call it phi of F, element of LQ star, defined as phi of F of G is the integration between F, G in the mu. This is well defined. So this map is really an element in this space, and it's linear. So it's a linear isometric embedding. So it preserves the norm. So every element is sent to an element with the same norm in this space. So it's an isometric embedding. Therefore, to prove that these spaces are exactly the same via this map, we only need to prove that this correspondence is surjective. So we are only left to prove surjectivity. Okay, so let's consider first the case in which the measure is finite, and then we will prove the case in which the measure is sigma finite. Okay, so first case is when mu is finite. Okay, so let's take an element, let's call it lambda, in the dual of LQ, and we want to represent this as an integration with respect to a map, a function in LP. Okay, since mu is assumed to be finite, then we have that whenever we take an element in the sigma algebra, then the characteristic is the characteristic of that set has finite integral, and also when we take the powers of it, so this is going to be an element in LQ, whatever it's saying. This is just because the Q norm, this is what it is. This is the integral of the function to power Q in the mu 1 over Q. But then this is just the measure of A to the power 1 over Q, and it's finite because the measure is finite. Okay, therefore, since this integral, this characteristic function is an element of LP, we can consider the value of the functional lambda on this function. So we can consider lambda of the characteristic of A. And so this is going to be actually a finite number, and let's define nu of A to be this value. Okay, the claim, first claim, is that nu is a real measure. We need to prove it. Okay, real measure on E. Okay, so let's prove the claim. So indeed, so first of all, what is the measure of the empty set? So this is by definition, this is the operator lambda to apply to the function characteristic of the empty set. The characteristic of the empty set is just the zero function, and since lambda is linear, this is zero. Okay, so the first condition to being a measure is satisfied. Second condition, suppose we have a sequence of sets A1, A2 in the sigma algebra that are pairwise disjoint. And let's consider A to be the disjoint union of this AN. Okay, now we want to see that the measure of this set is just the sum of the measures of these sets. Now, first of all, notice that if we consider the characteristic of the finite union up to n of these sets, this is a function that pointwise converges when n goes to infinity to the characteristic of A. Moreover, since this union is increasing, this convergence is monotonic. So they are monotonically converging from below to the characteristic of A. So we can apply the monotone convergence theorem. Okay. Now, okay, since Q is different than infinity, and the measure of A is finite, we have, let's change page. Okay, let's bound the LQ norm of the difference between the limit function and each of the function characteristic of A1 union AN. So let's take the Q norm, or let's take better the Q power of the Q norm. Okay, this by definition, this is the integral of the function to the power Q d mu, not P, Q in the mu. Now, this function here, this is, so this set is a subset of this, right? So it is 1 exactly if a point is in A but not in this finite union, and is 0 otherwise. So this is equal to the integral over A minus A1 union AN of 1 to the power Q. Okay, so therefore this is mu of A minus A1 union AN. And this, as n goes to infinity, this goes to 0. Remember that this fact, it is true under the assumption that mu is finite. Otherwise this may not be true. Okay, so we have therefore that this this limit goes to 0 as n goes to infinity. Okay, so hence what we have is that the characteristic of A1 union AN converge in LQ to the characteristic of A. Now we are going to use that lambda, the operator, is continuous. So since lambda is continuous, we will have that the value of lambda on these functions converge to the value on that function. So we have page. Okay, we have that nu A, which by definition was the integral, was lambda of the characteristic of A, and lambda of the characteristic of A is the limit of the characteristic of A1 union AN. Now, by continuity, so lambda is continuous. We have that this is the limit at n going to infinity of lambda of these characteristics. Now, since the AIs, AN are disjoint, we have that this the characteristic of the union is the same of the sum of the characteristic of each set, I from 1 to n. Now, since lambda is linear, we have that this is the limit of the sum of lambda of the characteristics of I, and this is by definition, again, this was nu of AI. From 1 to n, limit on n to infinity, and this is what we call the sum from I to 1 to infinity of nu of the AIs, right? So we prove that on these joint sets, the function is additive, and therefore we have proved that nu is a real measure. Next, we claim that this measure nu is absolutely continuous with respect to mu. And this is going to be easy. Indeed. So if we take a set in the sigma algebra with mu measure equal to 0, then the characteristic of A is equal to 0, to the function 0, as elements of LQ, right? Because LQ is the space of functions that are equal up to a set of measured 0, and up to A, these two functions coincide. So nu of A, which is by definition lambda of the characteristic of A, is equal to the characteristic of 0, and by linearity this is 0. Okay, so we prove that for any mu null set, it is every mu null set is nu null. Okay, great. So now we can apply the Radon-Nikodym theorem, or Lebesgue decomposition. So by Radon-Nikodym, which we saw as a consequence of Lebesgue decomposition theorem, we have that the measure nu can be expressed with respect to a function, which we call a density, that is in L1. So there exists f such that nu is f times mu. What does this mean? This means that for every set in E, nu of A, which by definition was the value of the operator on the characteristic of A, can be expressed as the integration of the function this density A with respect to the mu, right? So we can see it as the integral f characteristic of A d mu. And now the way we have to read now this equation is that, you see, on characteristic functions, we saw that the operator lambda can be expressed as the integration of the characteristic function with respect to when multiplied by a function f. Okay, so now what we have to see is that this function here is a function in LP, right? And then we need to show that this equivalence is not only for characteristic functions, but for all all the functions that are in LQ. Now, by linearity of the operator lambda and of the integral, now the equation is not only true for characteristic functions, but also for step functions. So if G is a step function, we have the lambda of G is equal to the integral of f G d mu. Okay. And notice that step functions are in all of the LP. But now, remember that if the measure of the whole space is finite, as in this case we are considering, then L infinity can be seen also a subset of LQ. And moreover, we have that if you have a sequence of functions that converge in L infinity, then they also converge in LQ. Okay, now we are going to use the fact that the step functions are dense in L infinity pay attention that the step functions are dense in LP is true when the measure is finite. Otherwise, it's not true. Huh? The measure is in this case is finite. Okay, so the function are dense in LP, of course, in the norm of L infinity. So dense in L infinity, in the norm of L infinity. Then what we have for all functions in L infinity, we can approximate the functions with the step functions in the norm of infinity, but in particular, those functions will also converge to the original function, not only in infinity but also in LQ. Okay, so this equation is true for step functions, and now we take the limit and get to any elements in L infinity. Okay, so again by continuity, hence by continuity of lambda, the operator, we have that the operator applied to this function g, so that maybe it's better, let's put the quantifier first. Then if g is in L infinity, then the operator on g is represented by the integration with respect to this function f. Let's call this equation star, because we are going to use it soon. Okay, so we have this this property, and now next claim is that the function f is a function in LP. And actually, the p norm of f is equal to the operator norm of LQ. Of course, operator as an element of LQ star. Okay. To prove this claim, we have to split the two situations when q is 1 or when q is greater than 1. So let's do the case when q is equal to 1. So p is equal to infinity. Okay, so we have to prove that f is in L infinity. So let's bound the integral over a of f in d mu. So as this we can see it as the integral of f characteristic of a in d mu, and we say that this is the operator applied to the characteristic function of a, which is less than the norm of the operator times the norm of the characteristic function as an element of LQ, which Q now it's 1. And so now this is So the one norm of the characteristic of A is just the measure equal to the measure of A. So we prove that the integral of this function is always bounded by the measure of the domain of integration times the operator norm, which therefore tells us that the function f, or the absolute value of f, is almost everywhere bounded by lambda. So for mu almost every x in E, and therefore in particular the f is in the L infinity of mu, with L infinity norm or essential sup bounded by the operator norm of lambda. Okay. So this was in the case when q is equal to 1. Next case, q in 1 infinity with the extreme excluded. So let's consider the function gn, which at point x is the sine of f of x times sine of f of x times norm of f of x to power p minus 1, characteristic of the set where f of x in norm is smaller than n. Okay, this is for x in E, obviously. Okay, and this was done in order for so first of all, the function gn is bounded by, so it's only non-zero on this set, and on this set f is bounded by n, and therefore this number is bounded by n to the p minus 1. So the function has an essential, a finite essential sup, right? So it's in L infinity. Thus, we can apply the equation star, this one here. Okay, let's apply on the next page. So what do we have? The integral of f x to power p, characteristic of the previous set where f is less than n in the mu. Then this, okay, by definition of the function g, so actually we define the function g in such a way that we have this, so f to the power p is f times gn, and including also these sets here. Okay, now by equation star, we have that this integral is equal to the value of gn. Now, because lambda is continuous, so it's bounded, then this is less than the norm of lambda times the norm of gn as element in the space LQ. And this is equal to norm of lambda times the integral of f to the power q. So the function was p minus 1, but times q. So it's q times p minus 1, characteristic of the set where f is less than n, d mu to the power 1 over q. Now, because P and Q are conjugate exponents, this number is just P. Okay, so let's write this as the yeah, just I'll write it as norm of P, P power integrated respect to this set, multiplied by this set, the mu 1 over Q. Now look that this number here is equal to the same number here. So now let's move it on the other side. Let's move it on the other side. So hence we have that the integral of f to the power p characteristic of the set where f is less than n, the mu to the power 1 minus 1 over p is less than norm of q, a norm of lambda. Okay. Now, first, again, since we have the p and q are conjugate exponents, this is nothing else than 1 over q. Moreover, these functions here, this function here, monotonically converges as n goes to infinity to the function f. So what we get is that this number here converges to the integral. So sorry, converges to LP, f to the p norm. So converge to f to the p. Converge to this. So here we have the mu, and then we had 1 over q. No, sorry, I did it wrong. So this was not p, was q. So this. Okay, so this was q, and therefore here was 1 over p, and here we have 1 over p. Okay, so now this is the p norm of f, which we prove that it's finite and bounded by the norm of lambda. So also in this case, we prove that f is an element of LP of mu. Let's summarize what we proved. We proved that for any lambda, there is lambda in LQ star, there exists an f in LP such that both functions g goes to lambda of g and g goes to the integral of f g d mu, these are elements of LQ star. So remember, we really proved that any function in LP gives you an element of the dual. Okay, so we proved that f is in LP. This is an element of the dual. This was by construction, by hypothesis, lambda was an element of the dual, but we chose f in such a way that these two operators coincide on step functions, actually even on L infinity functions, on step functions. Okay, now by density of step functions, in LQ, LQ, we have that the two elements, the two functionals coincides. Now let's draw the conclusion. Okay, so what we prove, therefore, we're done. Therefore, every element of or every element in LQ star comes as the integration of with respect to this is what I mean, okay, comes as one F, right? With respect to an element in LP with P the conjugate of Q. Again, it's important that Q is different than infinity. We'll see what happens when Q is infinity. This was the proof in the case lambda was a finite measure. Now, let's now discuss the general case when mu is a sigma finite measure. Okay, again, let lambda be an element of the dual of LQ. We have to represent it as an integration respect to a function f. Now, since sigma is sigma finite, since mu is sigma finite, there exists a n disjoint such that the whole space is the disjoint union of this an, and the measure of this an is finite. Okay. Now, notice that we have the notice that we can see the inclusions. Okay, so if I look at LQ of the space AN of the sigma algebra, okay, in this way it's just a symbolic way of saying take any element in E and intersect it with AN. Okay, with the measure mu restricted to AN, this can be seen as the space LQ of the whole space E, the whole sigma algebra, and the measure mu restricted to AN. And this space can be seen as subset of LQ of the whole space. This can be done where every G from AN to every function defined only on AN is extended by considering Gx equals 0 for all x in E but not in AN. And likewise, if we have a function in here, we can, this measure is supported on AN, so we can change it to be 0 outside of AN, and it still represents the same function in this space. So we have this isomorphism and this inclusion. Okay, so now this space here now it becomes a space with a finite measure. Like, or this one is a finite measure because of this assumption here. So now we can restrict our operator from this space to this space and apply the first case. Right? So this inclusion is not just setwise, but moreover, the inclusion is continuous. Right? Really, this is a topological subspace. So the inclusion is continuous. Actually, an embedding. Okay. Therefore, by the first part, by the first case of this proof, mu restrict an is finite measure is a finite measure. We have so we get that for any n there exists fn that are element in the LP space of E mu restricted to an, such that for all elements in the LQ space of E mu restricted to an, we can represent the operator on G to be the integration with respect to this function fn. Fn times the mu restricted to an. And we can also write this integral as the integral of the whole over an of G fn d mu. Okay, now we have to glue together these functions fn. So let's see this function fn as defined on the whole space, right? So we can, or they actually are, but outside of n, the complement of n is a negligible set. So we can change the fn as we like. So we can extend or redefine fn to be null on the complement of an. Okay, this way we have that since the space E was the disjoint union of the fn, we get we define f to be the sum of the fn, seeing as the limit, right, n going to infinity of the sum n from 1 to capital N of the fn. So of this fn has f disjoint support. Okay. So also from the first case, for the case when mu is finite, we also get that the LP norm of the fn were bounded by the operator norm. Okay. But also we can apply the operator, the first case, to the function mu restricted to a1 union an, which as a representative functions we would get n from 1 to capital N. Okay, this was capital N. So we have this bound for all n, and therefore we also have that f is in LP. Yeah. Okay. So this function here was in LP. Now let's just prove that the this function represents the operator. Okay. So what do we do now? Now take any element in LQ, and notice that if we now let's multiply G by AN. So AN is this decomposition of the space. And now if we sum up to N, this is just seeing G times, so this is the same of G times the characteristic of this joint union A1 to A capital N. And this sequence of functions is dominated by G. I mean, they converge also monotonically from below to G. So the sequence, but the dominated convergence sequence converge in LQ to G. And similarly, we have if you multiply Fn times G, and from 1 to capital N, this converges in L1 to Fg. Remember, right? So when you multiply an LP function and a Q function by Holder inequality, they are integrable. Okay. Now this is bounded by Fg, is dominated by Fg. So the integral, the limit integral is the integral of the limit. Okay. Now we are ready to prove that that this function f represents lambda. So hence, lambda of G, now by continuity of lambda, this is equal to the limit of lambda of the sum up to n of G characteristic of AI. We prove that this converges to G. So, and lambda is continuous. Good. So now lambda is linear. So I can swap the limit with the sum. N to infinity. Now, remember, so we have now that this function here is a function supported on a set of measured zero, of finite measure, right? So we know that we have the property of this space. Now this is a finite measure. So we know that on this set, the operator lambda can be represented as the integration of respect to the measure Fn de mu restricted to An. Okay, now this is therefore this is just the limit of the integral. Now let's move the sum inside again. This was an I from 1 to n of G Fi d mu. No, G is not here. Now, you know that this one is converging to F. So by the dominated convergence theorem, this is equal to the integral of G F T mu. Okay, in conclusion, again, every lambda is represented by some F in LP. LQ star is represented by some F in LP. And this is the end of the proof that for P different than infinity, but for any other, for Q different than infinity, LQ is isomorphically and isometrically represented by LP, when P is the exponent corresponding to Q.